Hi, this is Barrett Givens, and in this video, I want to talk about using the definition of a quotient topology to define a topology on a space with 3 points. Okay, and I'm going to do this by thinking of the real number line R, which I have pictured over here on the side, R, and I'm going to define a map from the reals to the set P and Z such that row of X is P if X is positive, N if X is negative, and Z if X is 0. Okay, so rho is clearly it's a surjection onto my X star, which is this 3-element set. And X is the reals. So my domain is the reals, that's my X. My codomain is this 3-element set, P and Z, which is X star. And then my function rho, which is onto, or a surjection, takes positive numbers to P, negative numbers to N, and 0 to 0. Okay, hence the names P, N, and 0. All right, now I want to figure out what are the open sets in X star. What are the open sets in X star? So what I will do is I will think about the inverse image of various subsets of X star. So first of all, what if I did the inverse image of just a singleton P? So just take the output P, look at that set that only has P in it. What is the inverse image? What are the points that get mapped to P? Well, the points that get mapped to P are all the positive numbers. So that's the interval from 0 to infinity. Is that an open set or not an open set? That's an open set in the usual topology. Okay, what about row inverse of Z? Just singleton Z. Well, the inverse image of Z, that's all the points that get mapped to Z. Only one point gets mapped to Z, which is 0. So that's just a single point in R. Is a single point in R an open set? No, not open. And then finally, what about row inverse of singleton N? That would be negative infinity to 0. That is open. Okay. And then we can think about other possibilities, like we can think about P and, I mean, there's only 8 here, so we can sort of just list them all. If I did P and Z, the inverse image of that would be the interval that includes 0 to infinity. That's not open. If I did row inverse of P and N, that would be negative infinity to 0 union 0 to infinity, which is open. And if I did Z and N, that would be the interval from negative infinity to 0, including 0, which is not open. And since there's 3 points, there should be 8 subsets, but the 2 that we're missing are the empty set and the whole space. Those always have to be in your topology. Those are always open. And so the open sets in this topology, the quotient topology on the set P and Z are empty set, first of all, singleton P, singleton N, P and N together, and then the whole space P and Z. Or if we wanted to write it kind of in the format that we sometimes drew some pictures when we first learned about these, if I draw it as 3 points, P by itself is open, N by itself is open, P and N together is open, but anything with Z is not open unless it's just the whole space. Okay, so that's an example of a quotient topology. One way that we often think about this is that we have identified points in this topology. So what we've done is we've taken all of the points that are positive and we've just smushed those down to be one thing, which is just the letter P. And then we've taken all the points that are negative and we've smushed those down to be one thing, which is the letter N. And then we have the point 0, which is still just a single point Z for 0. Okay, so we've sort of taken this topology right here, and we've just squished all of that down to being just a P, and we've squished all of that down to being an N, and we've just left Z as itself. All right. Thank you for listening.